Okay, so this video is going to cover 6.3 and 6.4. So 6.3 discusses line spectra and the Bohr model. Okay, so in 6.1 and 6.2 we talked about the fact that light has wave characteristics, meaning it has a wavelength and a frequency. Okay, and then we also talked about these chunks of energy called photon. So now we're going to take the idea that light are waves and these chunks of energy and talk a little bit more about how that relates to chemistry. Okay, so the line spectra is basically, you can have three different types of line spectra. So you can have a monochromatic, indicating that you're just going to have radiation of a specific wavelength. Okay, so for example, in this one, you see that the specific wavelength that we're talking about is somewhere between, it looks like it's closer to 600, so probably like 590 or something like that. Okay, so this is monochromatic, which means one wavelength is present. You can also have a spectrum, which is radiation separated into different wavelength components. Okay, so you've heard of our visible spectrum. Maybe you've heard about it in terms of Roy G. Biv. Okay, so red, orange, yellow, green, blue, indigo, violet. Okay, so the reason why we see different colors is because those different colors have different wavelengths. Okay, so a continuous spectrum here, you can see that I have all of the different colors, which indicates that I have all of the different wavelengths present. Now, line spectrum can be specific to us identifying different elements based off of the colors that they give off. So for example, if we look here, line spectrum is spectrum containing radiation of only specific wavelengths. Okay, so this would be a continuous spectrum. Okay, but we can also look here that sodium has only certain wavelengths on that spectrum. So that those wavelengths, those specific wavelengths are specific to sodium. So for example, it has two here, two here, two here, and one here, which means it has 2, 4, 6, 7 specific wavelengths specific to sodium. And then you see the same thing for the rest that are listed here. This is one way that we were able to identify that stars are made out of hydrogen and helium. Because when we look through a telescope at stars, we see the certain wavelengths being given off by those stars. Okay, so that's one way that scientists were able to identify what stars were made of. Okay, which leads us to the next idea, which is Bohr's model. Okay, so Bohr came after Rutherford. So if you remember Rutherford in first level chemistry, Rutherford is the dude that shot these particles through gold foil, and most of them went through, but some of them came back. So he identified the positively centered core nucleus. Bohr, so let me just read what this says. I'm sorry. So it says Rutherford discovered positive central core, but didn't account for the reason why the electrons didn't collapse on the central core. Okay, so Rutherford identified that we had the center positive, but he didn't talk about the electrons and why they weren't sucked into the center towards the nucleus. Because the law of gravity tells us that everything should sort of collapse on itself, but what was happening is that these electrons were not doing that. Okay, so along comes this guy named Bohr, and he stated 3 postulates to explain where electrons are in relation to the nucleus. He said only orbits of certain radii correspond to certain energy levels. Okay, so if you're close to the nucleus, you have a certain energy, and as you move away from the nucleus, you have a different energy level. He said electrons have a specific energy and its allowed energy state, meaning if it's in an energy level, it can only have that amount of energy. And then he said that energy is emitted or absorbed only as electrons change energy levels, which brings us back to what we talked about in section 6.2, which is the photon, okay? So if we look at the way that Bohr has this idea of electrons releasing and absorbing energy, what he's saying is that as the electrons move away from the nucleus, okay? So think about this. If you're holding a dumbbell, okay, it's a lot easier to hold the dumbbell close to you like this than it is to hold it away, right? After a while, your arms get tired, right? So it happens to the same thing with electrons. The further away the electrons get from the nucleus, the more energy that they have, okay? So what Bohr stated was, if you have an electron that's at a higher energy level, so like up here, and it falls back down to a lower energy level, that energy has to go somewhere, okay? And where is that energy being emitted? It's being emitted through a photon. So this right here is our energy is equal to Planck's times the frequency, okay? So as that electron goes back down, the energy that it loses from this energy level to this one has to go somewhere, okay? And that it goes somewhere in the form of light, okay? Which brings us to the next section, which is the wave nature of matter, okay? So we talked about the wave nature of light, meaning light has those waves, okay? Well, now we're going to talk about matter, all right? So we know that the wavelength is equal to Planck's times the mass of a substance times its velocity, okay? So I drew nu and I wanted a v, I'm sorry, times velocity. And this is mass. Okay, this is momentum. Passed electrons, so what happens is we pass electrons through a crystal and they diffracted just like X-rays would, okay? And we know X-rays are light, okay? So that indicates if that electrons pass through a crystal just like X-rays, and we know X-rays are light, and X-rays have waves, therefore by default electrons also must have waves present, okay? So brings us to our uncertainty principle. So if an electron has wave properties, how can we know where it is? Okay, we can't. This is the uncertainty principle. Okay, it is impossible to know the momentum, so the speed, and the location at any given time in an electron because they're too small and they move too fast, okay? And they're waves, right? We don't necessarily know where waves are at any given time because we can see the colors, but we don't see the waves of the colors, right? We just see them, okay? So electrons possess the same properties of a wave. So this gave us a brand new understanding of what an atom actually looks like, which brings us to the next section, which will be in the next video.